Swayam Prabha. Digital India. Educated India.
Welcome back in this module, and in this module we are discussing about another problem on the deflection of particles. So the collision, the elastic collisions of particle, and so the problem says the problem asks is what are the energies of the two electrons, energies of the two electrons after collision. Okay, so what we have is both the electrons. I'm assuming, since we are talking about electrons have the same mass, so essentially the particles which are colliding have same mass. That is important, right? So both electrons have equal mass, and collision is elastic. So that is given. Collision is elastic, right? And we see that the opening angle between the opening angle between the two particles, between the electrons, is 90 degrees. How can we say that? Because both electrons have equal mass, right? So we are using formula. What is the name of the formula? So we are using formula, this one, star. So let me call this as formula A. So using formula A here, we find that the opening angle is 90 degrees. So it's given that the incoming electron is observed to be deflected with an angle of 30 degrees. So let me try and draw the diagram here. So the incoming electron was M1. So this is deflected by an angle of 30 degrees, and the net deflection is 90 degrees. So this one is 90. So we expect that the recoil angle is 60 degrees, right? So the recoil angle, so if the scattering angle is 30 degrees, the recoil angle is 60 degrees. And now we can start to write the energies of the system. So let us say that u being the initial speed of the incoming electron. Right? And u1, u2 is the final speed of both electrons, right? Final speed of both electrons. And what we see is that the linear momentum in both the directions is conserved. So we have that the linear momentum is conserved in both x and y direction, right? And we see that if that is the case, m times u is m times u1 cos of 30. So this is, we are trying to conserve the linear momentum in the x direction. Okay, so m u1 times cos 30 plus m u2 times cos 60. Remember, momentum conservation is a vector conservation equation. So we have to conserve in each components. And then mu1 sine 30 minus mu2 Remember, the directions are as follows. So mu2 sine 60, this is equal to 0. And from here I see that E1 comes out to be 3 by 4 E, and E2 comes out to be 1 by 4 E, right? And that is what we have, where E1 will be half m U1 square and E2 is half m U2 square. Remember, we have two equations here, and in terms of the initial velocity U, I can solve for both U1 and U2 and write down the energy in terms of the initial energy, and that is what we get. Notice that the total energy E1 plus E2 is E, which is the initial energy, and hence the energy is conserved, and this is a lastic collision. Okay, so that is what we have. This question now is, we would like to, these are, so far we have just seen the case of lastic collision in a fixed frame, in a lab frame. Now, if we have more complicated collisions, say for example non-elastic collisions, then it is always convenient to look at this setup in a more convenient frame, right? So we would like to study this collision of two particles in a more convenient frame where certain quantities are set to 0. So we call this convenient frame as the so-called zero momentum frame, right? So we are going to revisit this collision in the zero momentum frame. Okay, so collisions in zero momentum frame, right? So zero momentum frame. Okay, so what we have is, so for an isolated system, so what exactly is zero momentum frame? So for an isolated two particle system, we see that the net force is 0, right? And which means that the center of mass G moves with a constant velocity, right? So for an isolated two particle system, the net force is 0, which means that the center of mass G moves with a constant velocity. So now we choose a frame G where the center of mass is at rest of the system, or the so-called zero momentum frame, right? So we choose a frame in which G is at rest, right? And this is the so-called zero momentum frame, right? So what we have is the linear momentum in this zero momentum frame. The linear momentum of both the particles combined is 0. So that is what we have, right? So which means that since linear momentum is a vector equation, if one particle is moving from in forward direction, the other particle will be moving in the backward direction, so as to negate the momentum, the net momentum, right? So so what we have is, in zero momentum frame, the total linear momentum of the two particles is 0, right? And let us say that V is the velocity of the center of mass, of course, velocity of then of the center of mass and in that case what we have is, we are going to move we are going to see from the center of mass frame, right? The center of mass has a velocity v, but if we sit on the center of mass frame, then we see that the center of mass is at rest, and that is the frame we are talking about, the zero momentum frame, right? So let's say that doesn't mean that the center of mass is not moving. So the center of mass is moving in a fixed frame with velocity v. That is what we are writing here, right? So v being the velocity of the center of mass. Then from linear momentum conservation, we see that the momentum of the system m times u1 is m1 plus m2 times v, right? This was the initial momentum m times u1, that is momentum of the approaching mass, and the final momentum is m1 plus m2 times v. So we see that the momentum of the center of mass is, the velocity of the center of mass is m times u1 divided by m1 plus m2. Okay, and this is the velocity of the center of mass frame. Okay, so that is what we have. And now let us talk about collisions here. So let us talk about, what sort of collisions we have. So let us say in the collisions, our initial linear momentum is P1 and P2, and our final linear momentum is P1 prime and P2 prime, right? Okay, so what we have is that P1 plus P2 is P1 prime plus P2 prime, and we see that this is conservation of momentum. Let us call this equation as star, and of course this is going to be zero. We are talking about the motion in the zero momentum frame, so the net momentum has to be zero in the zero momentum frame. Okay, so this also means that P1 is minus P2 and P1 prime is minus P2 prime, or P1 so essentially what the zero momentum frame tells us is that the momentum are equal and opposite, whether the initial momentum or the final momentum, right? Okay, so what we get is, now because because of this momentum conservation, we expect that the particles are going to get deflected by the same angle. Let's call this same angle psi, right? So there is no different recoil angle and scattering angle that we saw in the fixed frame calculations. This time in the zero momentum frame, we have just one angle of deflection, that is we call this as the angle of deflection, right? So because of star, because of linear momentum conservation, we see that the particles arrive and depart in opposite direction. And we see that each particle is deflected. Each particle is deflected through the same angle psi. Each particle is deflected through the same angle psi here, and so let me draw the diagram and it becomes clearer. So what have we got? So we have that P1 so P1 what we get is P1. Well, let me see what we have. So P1 prime, P2 prime, and we see that this is V1 by V2. So this is V1 and V1 prime. So V1 and V1 prime, and we have that we have V2. So remember, in the zero momentum frame, the velocities are equal and opposite. Otherwise, the momentums are not going to cancel. So the diagram looks like this. So V1 prime, and then in the opposite direction, we have V2 prime. And we can essentially, we will have the same angle psi. So this is psi, and the same angle here is psi here. The same psi, right? And we see that so if we were to write now the energy conservation, momentum conservation is very simple, right? But if we were to write the energy conservation in this frame, we see that energy conservation, right? So we see that P1, so half m1 v1 square plus half m2 v2 square plus q comes out to be half m1 v1 prime square plus half m2 v2 prime square, right? And now we see that, well, v1 v2 are the initial velocities and v1 prime v2 prime are the final velocities. So now what we get is so we already saw that P1 is minus P2 and P1 prime is minus P2 prime. So from there we can assume from so this is my momentum conservation. So we can assume that P1 the magnitude of P1 and the magnitude of P2 both are same, which is equal to P. It is only the direction which are opposite. So the magnitudes are same, and similarly we have the same thing for P2 as well. We see that this is equal to P, right? And we see that if that is the case, we see that P square, well now, well, let me call this as P prime. So this P prime can certainly be different from P. So now if we were to write the energy conservation, this equation in terms of the momentum, we see that this is equal to P square by 2m 1 plus P square by 2m2 plus Q is equal to P prime square by 2m1 plus P prime square by 2m2, right? And we see that P prime square is P square plus 2Q m1 by m2 by m1 plus m2, right? So so that is what we have, and let me call this equation as double star. So this is my energy equation. And then for elastic, of course, let us look at the special case for elastic collisions. So for elastic collisions, we see that Q is 0, and in this case P prime is P, and all, in this case, all momenta, if Q is 0, then we see that P prime becomes P, and then all momentas are equal. All momentas are equal, whether it is the initial momentum or final momentum of any particle, they are all equal, and that is a very trivial conclusion, right? And then but what are these momenta? That is something we will try and find. We see that in the lab frame, we see that the initial velocities are v1, which is u minus v, and v2, which is minus v, right? And we see that p, which is m1 v1, which is the incoming momenta, is going to be m1 times m2 u by m1 plus m2, right? So that is p. Okay, so so what have we got here? So the scattering process here, it turns out that the momentas are equal here, whether the collisions are elastic or not. The scattering process in this zero momentum frame is completely determined by q and psi here. So that is the beauty of studying this collision process in the zero momentum frame, because now we only have 2 degrees of freedom, which is capital Q and psi, right? So so what have we said? The scattering process completely determined by Q and psi, right? And we call this as the zero momentum, the psi as the zero momentum scattering angle, the zero momentum scattering angle, right? And of course, for elastic collisions, capital Q is 0, and of course psi becomes, without loss of generality, psi is 90 degrees. Okay, so let's see how much time have we got. I think this module gives us enough time, so that is where we would like to stop in this particular module. And in the next module, we will go back to our study about the collisions in the lab frame, right? And try to relate the various quantities from the from the zero momentum frame to the lab frame, and see what is the and see the comparison. So thanks so far for listening. Thank you. Welcome back, everyone. And in this module, we will be talking about our discussion on the lab frame, lab frame dynamics. So let me talk about back to lab frame, right? So this is, we will again, as usual, we will start our discussion on elastic collisions. So what have we got here is that let me try and draw the setup. The final the setup means the eventual position of the scattered particle after collision, both in the lab frame and the zero momentum frame. So we have the following. So U1, this is the U1 delta 1, and this is U2 delta 2, and we see that this is what we have. This is the lab frame psi, and well, this is the zero momentum angle psi. So psi will be the total angle here with respect to the horizontal, and we have that this psi is this following, and this is theta 2 here. Theta 2 is the recoil angle in the lab frame, and theta 2 is the following. And what we have is well, what are we missing here? Right. So the velocities are v1 prime after collision and v2 prime, and v1 prime is v bar, and here we have v bar, right? And that is it. So what we have is, so let us look at the observations in the lab frame. So final observations in lab frame, right? So let the zero momentum frame have the velocity v, right? So the final the zero momentum frame means the center of mass frame has velocity v. So which means that if the final velocities of the particles, in the lab frame is u1, u2, we see that the zero momentum, the final velocities in zero momentum frame is v1 prime, v2 prime. We see that u1 is v1 prime plus v being the velocity of the center of mass, and u2 is v2 prime plus v, right? And so now we see that, so these are the relation between the zero momentum frame final velocities and the lab frame. So we see that in elastic collisions, q is 0, or we have that all momentas are equal. That is what the conclusion was. All momentas equal. That was in the case of elastic collision, right? And in that case, we saw that v1 prime, the final velocity in the zero momentum frame for particle 1, v1 is going to be p, divided by m1, which comes out to be m2 u by m1 plus m2, right? And similarly, we see that v2 prime comes out to be m1 u divided by m1 plus m2. And if listeners can carefully notice that this is the same quantity that we found for the velocity of the center of mass, right? I think somewhere down the line we had also found the velocity of the center of mass. Let's see here. Notice earlier we had just found the velocity of the center of mass, and we found that v2 prime is the velocity of the center of mass. Okay, so then from here we can find the formula for the scattering angle. See, what we are doing here is we are using our zero momentum frame setup, where the calculations are relatively simple, and we are trying to find the formulas for the various quantities after collision, like the scattering angle, recoil angle, and so on, in the lab frame, right? So the scattering angle theta 1 here is given by tan theta 1. Tan theta 1 is v1 prime sine psi divided by v1 prime cos psi plus v, and this is going to be sine psi by cos psi plus v by v1 prime, right? And this is going to be sine psi by cos psi plus, well, v by v1, v by v1 prime is going to be, it's from these two relations, v1 prime, v2 prime. So v by v1 prime will be m1 by m2. So my scattering angle depends on the zero momentum, what is the name I have given? Zero momentum frame scattering angle. So my lab frame scattering angle is dependent on the zero momentum frame scattering angle as follows, which is here, right? So that is what it is. Okay, so then from geometry, from, let's say we call this as figure 1. Say from figure 1 we see that the recoil angle can be found similarly. The recoil angle is given by theta 2 is pi by 2 minus psi by 2, right? So the recoil angle is 90 degrees minus, well, remember the total angle, we are talking about elastic collisions here, so theta 1 plus theta 2 must be equal to pi, right? And so that is where this, sorry, theta 1 plus theta 2 must be equal to pi by 2. So that is where this pi by 2 is coming from, right? So theta 2 comes out to be, well, I can rather not find recoil angle but the opening angle, and from there I can find the recoil angle. So the opening angle theta is such that tan theta is theta 1 plus theta 2 is m1 by m1 plus m2 divided by m1 minus m2 times cot psi by 2, right? So I have used these various relations for recoil and scattering angle, and this is what we find. Okay, so then I can also use, I can use v2, let us see, v2 u2. Let us look at this particular triangle, the lower triangle, where one side is of magnitude u2, the other side is of magnitude v2 prime, and this triangle is an isosceles triangle with same angle theta 2, and I can write, well, I can write the angle here. So using sine rule, I see that v2 prime by sine theta 2 is u2 by sine psi. So that is what we have used in this triangle that I have circled. We have used the sine rule. So v2 prime by sine theta 2 is equal to u2 by sine psi, and from here I see that u2 is 2v sine psi by 2, right? So 2v sine psi by 2. Okay, so we have also used the formula for v2 prime and v1 prime in eventually finding out this relation which is circled. So then we can also find the energies, right? So the total energy after collision for, let's say, particle 2 with respect to the initial energy E0 is going to be half m2 u2 square divided by the total energy half m1 u square, right? And again we plug in all these values of u2 and the other values, we see that this is equal to 4 m1 m2 by m1 plus m2 times sine square psi by 2, right? And of course, this is elastic collision, so we have that E1 is E0 minus E2. So these are my final energies, right? Final energies. Okay, so let us recap everything here. Let us recap all the formulas that we have so far seen. So, what we have is, this is the elastic collision formula. So what we have is tan theta 1 is sine psi by cos psi plus gamma, and tan and theta 2 is half pi minus psi, right? So these are my scattering and recoil angles, where gamma is m1 by m2. Okay, and then my total angle, so this is my total angle is theta, such that tan theta is coming out to be gamma plus 1 divided by gamma minus 1 times cot psi by 2, cot psi by 2. So the first relation is the scattering angle. The second relation is the recoil angle, and the third relation is the total angle, right? And then the final ratio of the energies, E0 E2 by E0, is 4 gamma by gamma plus 1 square sine square psi by 2, right? So this is the ratio of the energies. Of course, E1 is going to be E0 minus E2, and so these are my the various formulas for the elastic collision. So let us try and utilize these formulas in some examples to see how they are applicable. Okay, so let us look at an example. So a particle of mass m and energy E is used to bombard stationary target of mass 2m, right? And we see that the problem says, suppose the final energy of one particle is E by 3, right? At what scattering angle will they find such particles? Okay, so basically the problem asks us to find theta 1 scattering angle, right? Okay, so we are given that the particle is of mass, the particles are given of mass m and 2m. Stationary particle is of target 2m, right? So 2m is our mass m2, because that is the stationary mass, and the moving mass is mass m1, right? So final energy is given to be E by 3. We expect that the particle of lower mass will have lower energy, right? We are talking about elastic energy. So one particle has final energy to be E by 3, the other particle has final energy 2E by 3. So it is the mass m1 which has energy E by 3, which is the lower mass, right? So that is the logic here. So we see that E1 by E0 is given to be 1 by 3, right? Where E0 is capital E. Okay, and E2 by E0 is 2 by 3, right? And if we use this formula, you know, we have a formula here, formula D. So we use formula D here. We can find that gamma comes out to be half, right? Gamma comes out to be, well, no, gamma is already half. Gamma is given to be half. Why? Because the masses are m and 2m. The masses are m and 2m. So if we have gamma equal to half and the formula is 2 by 3, if we use formula D, we get that using formula D, we get that 8 over 9 sine square psi turns out to be 2 by 3, or my psi comes out to be 120 degrees. The zero momentum scattering angle comes out to be 120 degrees. And then we want to find the scattering angle theta 1. So the scattering angle theta 1 is formula A. Remember, formula A contains gamma, which is already given, and psi. So that was the whole idea, to use formula D so that we can find psi. So the moment we know psi and gamma, we can immediately find what is theta 1. And so from formula A, we see that tan theta 1 is infinity. We plug everything and we see that this is infinity, or theta 1 comes out to be 90 degrees, and essentially the scattering angle is perpendicular to the incident beam. So if the incident beam was, so m1 was hitting m2 incidentally here, then the scattering angle is such that m1 is deflected at an angle of 90 degrees with respect to the incident beam. So that is the conclusion here. So theta 1, the scattering angle is perpendicular to the incident beam. Here, right? Okay, so then let us quickly look at one more example before we recap. In the second example, we have another collision. So in another collision, the opening angle is given to be, 45 degrees, is given to be 45 degrees. What are the individual scattering and recoil angles? Okay, so what we get is theta is 45 degrees. It is given that the total opening angle is 45 degrees, and from let us see what are the formulas here. We have the total angle formula, which is formula C. From here we can find psi given gamma. So from formula C, we see that cot psi by 2 comes out to be 1 by 3, or psi by 2 is 72 degrees. Okay, so that's what we get. Gamma is 1 by 2 already given, and so from here psi by 2 is 72, and theta 2, well, we can immediately use formula number B here to find what is theta 2 from psi. So from formula B, we can find theta 2, which is 90 degrees minus psi by 2. Well, psi by 2 is 72, so 90 degrees minus psi by 2, which is 18 degrees, and that is my theta 2, or the recoil angle. And now from here we can immediately find what is the scattering angle. The scattering angle will come out to be theta minus theta 2, where theta is 45 degrees and theta 2 is 18 degrees. So I see that theta 1 is 27 degrees. Okay. So so that's how we use all these various formulas using, of course, these are for elastic collisions, right? Here is one more quick example before we wrap up. The third example says, in another collision, the scattering angle was found to be 45 degrees, and what is the recoil? What is the recoil angle? Right, the scattering angle was found to be 45 degrees. What is the recoil angle? We can again, the scattering angle means the angle theta 1 is to be 45 degrees. What is the recoil angle? So again we can use formula A of scattering angle. Formula A. Remember, in all these examples, the ratio of the masses gamma is 1 by 2. So that is something which is common. So from formula A, we see that 2 cos psi minus 2 sin psi is 1, or we see that from here we can simplify this equation as cos of psi plus pi by 4 is equal to 1 by square root 8, and from here we can find that psi is 24 degrees. Okay, and we want to find recoil angle. Recoil angle is 90 degrees minus psi by 2, or this is going to be 90 minus 12 degrees, which is 78, right? So my recoil angle is 78. This is from formula B. Okay, so that's the ease of using all these formulas when we have already figured out our calculations in the zero momentum or collision frame, right? So we wrap our discussion, at least for the first part of the conservation principle, or the conservation of linear momentum for a system of particles. And in the next part, in the next module, we will continue our discussion and we will introduce the concept of the so-called reduced mass. So thank you very much, and thank you so far for listening.